All right, welcome back. This is just some bonus content, I guess, for section 1.8. So God bless you if you're here. um, but I just want to quickly cover a couple topics that they're not primary things that we need to focus on in the course, but I think they would be naturally things that would come up. I think if you're a kind of a curious person. So let's kind of dig into a couple things. First of all, I want to talk about relative measures of dispersion. So in 1.8, we talked about measures of dispersion: standard deviation, IQR, IQV. And we can use those things to determine how much variety there is in a data set. Okay. And when two data sets have the same mean, then comparing the standard deviations of those two data sets can tell us which one has more variation. But I think a question naturally arises if you want to compare the variation in data sets that have different means, especially if the means are vastly different. Because in that case, it really wouldn't be the best thing to compare their standard deviations. What we should actually do is compare their standard deviations relative to their corresponding means. And to see why, I think this example is really helpful, right? So you might consider the weights of dogs versus African elephants, right? Dogs have an average weight of 40 pounds with a standard deviation of 20 pounds. Elephants have an average weight of 12,000 pounds with a standard deviation of 1,000 pounds. Now, if you think about what you know about dogs have a lot of weight variety. There are really small breeds of dogs like Chihuahuas, and then there are very large breeds of dogs like Great Danes, okay? Whereas African elephants, on the other hand, if we're just talking about, let's say, adult male African elephants, there's not going to be as much variety. Sure, there's going to be some variation in their sizes, but they're going to be relatively close to the same size, right? And yet the data don't show that if all you're doing is looking at the standard deviations, right? So if at first glance, we might incorrectly conclude that elephants have more weight variety since their standard deviation is so large, right? 1,000 pounds compared to a standard deviation of just 20 pounds for dogs. However, the only reason that elephants have such a large standard deviation is that they are very large animals to begin with. Okay, relative to their size, 1,000 pounds is not actually all that much. Okay, in other words, if an average elephant is 12,000 pounds already, then a standard deviation of 1,000 pounds isn't very much. Whereas for a dog, where the average weight is only 20 pounds or 40 pounds to begin with, then a standard deviation of 20 pounds is huge, right? Their standard deviation is half of their average weight, right? Which is a lot of variety relative to their size. So this leads us to discuss what's called the coefficient of variation, or CV. The CV is the amount of dispersion in a data set relative to the mean of the data set, right? And it's calculated by dividing the standard deviation by the mean. So if you had population data, then you would do sigma divided by mu. If you had sample data, you'd do S divided by X bar. But either way, it's the same. Standard deviation divided by mean. So let's look at this example, right? Dogs have an average weight of 40 pounds with a standard deviation of 20 pounds. African elephants have an average weight of 12,000 pounds with a standard deviation of 1,000 pounds. Which species has more absolute weight variety, and which species has more relative weight variety? Well, African elephants clearly have more absolute weight variety. Just in absolute terms, 1,000 is more than 20, right? But relative to their average size, right? So which species has more relative weight variety? Well, for that, we'd have to calculate the CV, right? So we can compare dogs versus elephants. Okay, the CV for dogs is going to be standard deviation divided by mean. So for dogs, that would be 20 divided by 40, which is 0.5. Okay, for elephants, the CV is going to, again, be standard deviation divided by mean. In the case of elephants, that's going to be 1,000 divided by 12,000. And let's see, 1,000 divided by 12,000. I'm just punching this into my calculator. That comes out to about 0.083. Okay, so now to answer the questions, elephants have more absolute weight variety because their standard deviation is larger. However, dogs have more relative weight variety because their coefficient of variation, their CV, is larger. And I think that's a more satisfying answer, right? If you think about, again, if you think about elephants, I think they're pretty consistent probably with their weights. There's going to be some variation, but not very much, right? Whereas dogs, there's a huge amount of variety in their weights, right? Okay, so that would be a relative measure of dispersion if you had a symmetric data set. Now, if you had a skewed data set, then we would need to develop some kind of relative measure of dispersion for skewed data. And there are lots of potential candidates for this. One of them that I've found is the QCV. This is the quartile coefficient of variation. That's the formula for it. I'm not going to give you an example of it in action, but just so you're aware that exists. And in fact, statisticians are coming up with new measures for things all the time. But that's one way that you could potentially compare the dispersion in skewed data sets, right? As for categorical data sets, the IQV, which we've already discussed, is actually already a relative measure of dispersion. So there would be no need to develop anything new for categorical data. Although I should mention that there are other ways to measure dispersion for categorical data sets besides the IQV. The IQV is just the one that I've chosen to introduce in this class. Anyway, so that's just a little bit about relative measures of dispersion. The second kind of bonus topic is just a quick derivation of the standard deviation formula. Because again, you may have seen this formula when we were doing section 1.8 and thought, well, but like, what is that? Like, where does it all come from? What does it all mean? So recall that the standard deviation is an attempt to measure the average amount by which each observation deviates from the mean. It's an attempt to capture the average distance from the mean for each observation. The reason that this formula does the trick is because in order to find the average distance from the mean, we would first need to figure out how far each individual observation is from the mean. We call this the deviation about the mean. So let's say that we have some observation x sub I, right? The deviation about the mean for that observation is going to be x sub I minus x bar, right? That's how far away xi is from x bar. We would do that for every observation in the data set. So for all of the xi's in the data set, we would do xi minus x bar. Once we have those individual deviations about the mean, we can compute their average, right? Their mean. But there's a slight issue here. Let's say that we were working with the data set 1, 2, 3, 4, 5, 6, right? Know what happens when we compute the mean of the deviations for this data set. To do this, first of all, we would need to know what the mean is. which I think you can probably intuit the mean here is going to be 3, but just to check, right, we would do 1 plus 2 plus 3 plus 4 plus 5 plus 6, and then divide by the number of numbers, which is 6, okay? And let's see, 1 plus 2 plus 3 is 6, 4 plus 5 is 9, so that's 15, and then 6 more would be 21. Oh, I didn't do that right, did I? 1 plus 2 is 3, plus 3 more is 6, plus 4 more is 10, plus 5 more is 15, plus 6, yeah, that's right, 21. Okay, and then 21 divided by 6. Oh, is 3.5. Well, it's a good thing we actually did the math, because I would have led you astray and said that it was that the mean was 3, but it's actually just it's actually 3.5, right? Okay. So now if we try to compute the mean of the deviations, well, first of all, let's get the individual deviations. So we'll get the deviations, right? That's going to be xi minus x bar. 1, 2, 3, 4, 5, 6. Okay. So what we want to do is do the deviation minus the mean, right? So that's going to be negative 2.5 in this case. Deviation minus mean. So that's negative 1.5. Deviation minus mean, negative 0.5. And so forth. Whoops. Okay. So these are the individual deviations about the mean. And what we want to do is calculate the average of those, right? So we want to average those up. So we would add them up, right? We would do negative 2.5 plus negative 1.5 plus, by the way, this is not what we do when we compute the standard deviation. I'm just saying, like, intuitively, this is probably what you would think to do, right? You would add these up and then divide by the number of values here, which is 6, right? But notice that when you do that, all the negatives are going to cancel the positives, right? So negative 2.5 is going to cancel positive 2.5. Negative 1.5 cancels that. This cancels that. We're just going to get 0, right? So this is just going to be 0 divided by 6, which is just 0, right? I'm putting a sad face because because if we wanted to compute the average deviation, we're saying the average deviation is 0. And that's not just an accident, that's always true. The sum of the deviations about the mean is always 0. Okay, so we've got to figure out something to do, because obviously if we always get 0, that's not going to be a very helpful summary, right? So what we need to do is make all of the deviations positive. And there are a couple ways to do that, right? The way that we do that when we're computing the standard deviation is that we square each of the deviations. What we could maybe do instead is take absolute values. And in fact, that does lead us to a useful statistic called the mean absolute deviation, or MAD for short. The mean absolute deviation is not used very often in statistics for reasons that are sort of beyond the scope of the course. Basically, it has to do with how mathematically useful the mean absolute deviation is versus the standard deviation. It just turns out that the standard deviation is more useful mathematically, right? If you've had calculus, it's basically because f of x equals x squared is differentiable and hence optimizable, while f of x equals absolute value of x is not, right? So anyway, so it's just mathematically easier to work with the standard deviation rather than the mean absolute deviation. And so what we're going to do is square the values. We're going to square all of the values to make them positive. So after squaring the deviations, then we can calculate the mean of the squared deviations. And then finally, we sort of, I say undo, but it should really be in quotes, we sort of undo the squaring by taking the square root. And that's why this is the formula for the population standard deviation, right? We compute the individual deviations about the mean. We square them to make them positive. And then we find the average of those squared values by adding them up and then dividing by the number of values. And then finally, we undo the squaring by taking the square root at the end. So that's how we get to the formula for the population standard deviation. Now, for the sample standard deviation, we divide by n minus 1 instead of by n. And again, that's something that's sort of beyond the scope of the course to talk about why. Basically, if we divided by n rather than by n minus 1, we would be underestimating the true population standard deviation. And there are a couple ways to see why mathematically that's the case. If we divided by n, so if we just had this, we would call this a biased estimator. And so if you're interested, you could Google biased estimators, right? But what that means is that it's just a systematically bad estimate. Dividing by n minus 1 instead turns out to correct for that error, so that when we divide by n minus 1 here, we get an unbiased estimator, right? So you could Google biased estimator, or you could watch this video, right? Which gives a fairly decent explanation of that. Another kind of mathematical reason why divide by n minus 1 instead of by n is due to a concept called degrees of freedom. And here, so you could Google degrees of freedom, or you could look up this video, which I think explains things really well from that point of view. But anyway, that's the derivation for those standard deviation formulas. So that's all I have to say for the little bonus content of section 1.8. So you're awesome, and I will check in with you in section 1.9.